Hello everyone, this is Nikhila Tippannavar from Arihant Arts, Commerce and Science Junior College, Bowdhan, Pune. Today we are going to learn about inner transition elements, that is F-block elements. They are also known as lanthanoids and actinoids. Inner transition elements. The elements in which differentiating electron enters into n-2 f orbital are known as F-block elements. Elements whose f orbitals get filled up by electrons, they are called f-block elements. These elements are placed separately at the bottom of the periodic table. They are a subset of 6th and 7th periods. Since f orbital lies much inside the d orbital in relation to the transition metals, the f-block elements are called as inner transition elements. These elements have 1 to 14 electrons in their f orbital, 0 or 1 in the penultimate energy level, and 2 electrons in the outermost orbital. The lanthanoids are characterized by gradual filling up of 4f orbital and actinoids by 5f orbitals. There are 14 elements filling the f orbital in each series. The relative energies of the Nd and n-1 f orbitals are very similar and are sensitive to electronic configuration. Now we will see the properties of f-block elements. Their properties are similar to the d-block elements. Electrons are added to f subshells of n-2 level placed between n-1d and ns block elements. Lanthanoids begin with atomic number 57 and end at atomic number 71. Although historically lanthanoids are termed as rare earth elements, they are fairly abundant in Earth's crust. For example, thulium is found more in abundance than silver. The name rare earth elements was coined because of difficulty in extracting them economically in pure form from other lanthanoids having similar chemical properties. But nowadays, due to newer separation methods like ion exchange resins, the separation of these elements has become easier and more economical. These metals are soft with moderate densities. They have high melting and boiling points. Similar to group 1 and 2, lanthanoids in the metallic state are very reactive and resemble alkali and alkaline earth metals in their reactivities. For example, they react with water to give the metal hydroxide and hydrogen gas. Oxidation state. The common oxidation state for lanthanoid is +3. The +2 oxidation state is also important. They all form stable oxides of the type metal oxide, where M is the metal ion. Higher oxidation states are unusual for lanthanoids, with the only exception of cerium, which forms a stable +4 species. Heat of atomization. The energy required to break up the metal lattice is heat of atomization. Lanthanoids have lower heat of atomization than transition metals. This is because with d electrons, transition metals are much harder and require high heat of atomization. The ionic radii. The ionic radii decreases from 117 picometer of lanthanum to 100 picometer for lutetium. This is because of 5f orbitals do not shield the outer 5s and 5p electrons effectively, leading to increase in effective nuclear charge and decrease in the ionic size. Such large ions have higher coordination number that varies from 6 to 9, 10 and up to 12 in some cases. For example, hydrated lanthanum ion is a nonahydrate. All the lanthanoids form hydroxides of the general formula LnOH thrice, where Ln represents any elements of lanthanoid series. These are ionic and basics. Since the ionic size decreases from lanthanum to lutetium, the basicity of hydroxide decreases. LaOH thrice is strongest base while LuOH thrice is the weakest base. Lanthanoids react with nitrogen and halogens to give nitrides and halides of the formula LNNN and LnX3 respectively. By doing so, lanthanoids lose their outermost 3 electrons to form stable compound in +3 oxidation state. In +3 oxidation state, many of the lanthanoids are colored, mostly green, pink and yellow. This is attributed to the electronic transition among the f orbitals. Like transition metals, the electronic spectra of lanthanoids, however, do not get affected with different ligands. Now we will see lanthanoids from electronic configuration point of view, oxidation state, color of spectra, their properties and applications. The electronic configuration of lanthanoids is xenon 4f0 to 14, 5d0 to 2 and 6s2. This is because the electronic configuration is 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d10, 4p6, 5s2, 4d10 and 5p6, and it is the electronic configuration of xenon. So we can simplify the electronic configuration of lanthanoids by xenon 4f0 to 14, 5d0 to 2 and 6s2. The lanthanoids involve gradual filling of f orbitals. The energies of 5d and 4f orbitals are very close. For lanthanum, 4f is slightly higher in energy than 5d. The lanthanum has electronic configuration of xenon 6s2 5d1 and not xenon 6s2 4f1. The table shows the electronic configuration of lanthanoid series from lanthanum to lutetium. It has been observed from the table gadolinium and lutetium have 5d1 electron to make f orbital half filled and full filled respectively, which render them an extra stability. The electronic configuration of lanthanides have variable occupancy in 4f 0 to 14 orbitals. Number of electrons in 6s orbitals remains constant in the ground state. The valential electronic configuration of these elements thus can be represented as n-2f 0 to 14, n-1d 0, 1, 2 and ns2. Next, we will study ionization enthalpy. What is meant by ionization enthalpy? It is the amount of energy required to remove the most loosely bound electron from an isolated gaseous atom. The first ionization energy of the element A is the energy required by an atom to form A plus ion by removing first electron from its valence shell. Similarly, the second ionization energy of the element A is the energy required by an atom to remove second electron from its valence shell to form A2 plus ions. And third ionization energy of the element A is the energy required by an atom to remove third electron from its valence shell. The table shows first, second and third ionization enthalpies of lanthanoids. Oxidation state. The +3 oxidation state is common to all elements in which 2 electrons of S subshell and 1 from D or F subshell are removed. The 4f electrons are strongly screened by inner electrons of 5s and 5p electrons. Thus, 4f electrons are not involved in the bonding. Besides these, some lanthanoids show oxidation state of +2 and +4. They are formed in case of F0, F7, F14 configuration or resulting ions. These are cerium 4+, ytterbium F14 and so on. Color and spectra. Some trivalent ions are colored in solid state as well as in solution. The color of lanthanoid ion is due to FF transition, which correspond to energy in the visible region of the electromagnetic spectrum. The color of ions having NF electrons is about the same as those having 14-n F electrons, where n is an any integer between 1 to 13. The table shows the lanthanum ion, number of electrons, number of F electrons and color. Now we will see the lanthanoid contraction. What is meant by lanthanoid contraction? As we move along the lanthanoid series, there is a decrease in atomic and ionic radii. This steady decrease in the atomic and ionic radii is called lanthanoid contraction. As we move from one element to another, the nuclear charge increases by 1 unit as 1 electron is added. The new electrons are added to the same inner 4f subshell. Thus, the 4f electrons shield each other from the nuclear charge poorly owing to their diffuse nature. With increasing atomic number and nuclear charge, the effective nuclear charge experienced by each 4f electron increases. As a result, the whole of 4f electron shell contracts at each successive element. The figure shows ionic radii of lanthanoids in +3 oxidation state. It clearly indicates decrease in ionic radii as we move across. Now we will see the properties of lanthanoids. Soft metals with silvery white color and moderate densities. Color and brightness reduces on exposure to air. Good conductors of heat and electricity. Except promethium, all are non-radioactive in nature. The atomic and ionic radii decreases from lanthanium to lutetium. This is known as lanthanoid contraction. Coordination numbers usually are greater than 6, typically 8, 9, 10 up to 12. The lanthanoids are strongly paramagnetic. Gadolinium becomes ferromagnetic below 16 degrees Celsius, and the other heavier lanthanoids, terbium, dysprosium, polonium, erbium, thulium, and ytterbium become ferromagnetic at much lower temperature. Magnetic and optical properties are largely independent of environment. Applications of lanthanoids. The lanthanoid compounds are present in every household. It is inside the color television tubes. The inside surface of a television tube or computer monitor is coated with tiny patches of 3 different lanthanoid compositions to give 3 colors that make the color image. The optoelectronics applications use lanthanoid ions as active ions in luminescent materials. The most notable application is the ND-YAG laser. Erbium doped fiber amplifiers are significant devices in the optical fiber communication systems. Lanthanoids are used in hybrid cars, superconductors, and permanent magnets. Now we will see the actinoids. Their electronic configuration, oxidation state, properties, and applications. First, we will see the electronic configuration in actinoids. The actinoid elements belong to the second inner transition series in which electrons enters in 5f orbitals. The electronic configuration of actinoids is not definite. The valence shell electronic configuration of 5f elements is represented as 5f 1 to 14, 6d 0 to 1, 7s2. The last row of elements in the periodic table is the actinoid series. It begins at thorium Z is equal to 72 and ends at lawrencium Z is equal to 103. Most of these elements are not found in nature. They are radioactive and man-made. Now we will see the oxidation state in actinoids. Unlike lanthanoids, they exhibit a range of oxidation numbers in their compounds which varies from +2 to +8. The most common oxidation numbers of the actinoids are shown in the below figure. The electronic configuration of actinoids is radon 5f 0 to 14, 6d 0 to 2, 7s2, where radon is the electronic configuration of radon. Rn indicates radon. As seen from figure, the most stable oxidation state in actinoids is +3. The highest common oxidation state of early actinoids reflect the loss of all outer electrons, which is similar to transition metals than lanthanoids. For example, uranium has electronic configuration of radon 7s2, 5f3, 6d1. The formation of +6 oxidation state corresponds to an electronic configuration of radon. Now we will see actinoid contraction. The ionic radii decreases as we move across the series, which is known as actinoid contraction. This is attributed to poor shielding offered by f electrons. The figure indicates the contraction of ionic radii of lanthanoids as well as actinoids. Now we will see the properties of actinoids. Similar to lanthanoids, they appear silvery white in color. These are highly reactive radioactive elements. Except promethium, all are non-radioactive in nature. They experience decrease in the atomic and ionic radii from actinium to lawrencium, and it is known as actinoid contraction. They usually exhibit +3 oxidation state. Elements of first half of the series usually exhibit higher oxidation states. Applications of actinoids. We have seen that the half-life of natural thorium and uranium isotopes are so long that we get very negligible radiation from these elements. We find them in everyday use. For example, thorium oxide TiO2 with 1% of cerium oxide was used as a major source of indoor lighting before incandescent lamps came into existence. Only because these oxides convert heat energy from burning natural gas to an intense light. Even today, there is a great demand for these lights for outdoor camping. Thank you, everyone.